Sorry. Yeah. So as I was telling, this course CH425 is called Chemical Bond and Molecular Geometry. This is meant for first year MSc and third year BS students. On the other hand, we have CH812. This is called Fundamentals of Quantum Chemistry, and this is meant for first year PhD students. So PhD students. So now the point is CH425. Whoever takes CH425, he or she cannot take CH812 in the next year because these two courses have 80% overlap. They're very common, 80% common, and towards the end 812 would have 20%, which is different from 4 to 5. Okay, so we are not going to allow someone who has taken 4 to 5 earlier to take this course, CH812. And CH812 is also designed in such a way that we train a pool of teaching assistants, TAs, for the first year course CH107, which is the introductory physical chemistry course. And a big part of that course is quantum mechanics in chemistry. So the theme of this course, CH425 and CH812, is the same. And the theme is quantum mechanics in chemistry. So I have already sent you emails on Moodle. So I hope that everybody have got it. And the email had links to 2 videos. And these are video lectures by Professor K.L. Sebastian, who is our distinguished visiting professor. And these 2 video lectures are on introductory quantum mechanics. So because the course is all about quantum mechanics and then eventually application of this subject to chemistry. So you should go to that YouTube videos and please watch those YouTube videos. And I'm sure that many of you have watched it. Today, we are not going to discuss those videos much, but I'm going to present for say 10 minutes or 15 minutes to give an overview of the course. Okay. Now for this course, we have 5 TAs. So far, we have 5 TAs, and all of them are online. And we have a WhatsApp group. They are also there in the WhatsApp group. So we'll interact through Google Meet, mostly Google Meet, and Moodle. So all the materials will be sent on Moodle. All the online interaction sessions would be on Google Meet, and the sessions will be recorded and then distributed. And every week, I'm going to send links to videos which are pre-recorded, mostly by Professor K.L. Sebastian. You must go and watch those videos and come and participate in this interactive session, so that you can discuss this, and then we'll also learn from those videos, and I will also give some presentation which will be recorded. Okay. So now what I'm going to do, I'm going to take names of TAs. So we have already taken, but we'll take names of TAs one by one. So let me take Asha Rani Chaudhuri. I think she is there. So can you briefly tell us about you?
Yes, sir. Good morning to all. I am Afran Chaudhary. He is a student working in Rajarshi Chakravarti's lab. So first I am taking this course as TA. I have done my TA in CH107 already. So let's hope for the great experience.
Okay, thank you. And you can contact them on WhatsApp.
Yeah, you can contact me on WhatsApp.
Also through Moodle. Yeah. So next is Praveen Kumar. Praveen, are you there?
Yeah. Myself Praveen Kumar, and also PhD 4th year student, and I have done already 107 course as a TA, and this is my first course as a TA.
For this particular course, okay. So next one is Rajiv Lochan Shahu. Rajiv, are you there?
Yes, sir.
Okay, so please introduce yourself.
Hello, sir. Good morning to all. Good morning to all. Myself Rajiv Lochan Sahu. I was already TA for 107 course. This was first time I was a TA for CH 812 and 425. Uh, Hope all will contact us regarding this course. And best wishes.
Okay. So next one is Ligesh.
Thank you.
Ligesh, are you there?
You don't need to say that whether you have done a TA in 107. It's irrelevant.
Okay. Yeah. Ligesh, are you there? Ligesh, are you there?
Yes, sir. Yes, sir. Yeah. Hi, all. I think
Yes,
I'm
very much.
audible, right?
You are.
Hello. Yeah. Hi, myself Likesh. I'm working with Professor Rajshri Chakrabarti. Hope this will be a nice experience. Thank you.
Yeah. Next one is Anish. Anish Chakraborty. Anish, are you there?
Yes. Yeah, myself Anish Chakraborty, and I am a research scholar from Professor Rahul Mitro's lab, and this is my first PhD for this CH425.
Also a 812. Yeah. Okay. So
Yeah,
thank you very much. So thank you very much. So before I start my presentation, which is very short, so let me ask how many of you have been uh, uh, introduced the subject of quantum mechanics? Hello? So is there anyone who has not been taught this subject, quantum mechanics?
So, hello sir, this is Aishwarya here.
Yeah, so you have never taken a course on
Yes.
quantum mechanics?
No, sir, I'm a bioinformatics student, so I haven't learned the
Okay,
subject.
what is your mathematics background?
I am a BSc in chemistry and I have 12th level mathematics. I have done 12th level mathematics.
No mathematics in BSc.
No, sir.
Okay, so
No, sir.
we'll work together hopefully. Anyone else who did not have any course on quantum mechanics?
Thank you, sir.
Yeah, thank you. Anyone else other than Aishwarya? Other than Aishwarya, is there anyone? Yeah, Shamikshan, so you did not have a course on quantum mechanics?
No, sir.
Okay, okay. You are in which? So you are in PhD student or what? MSc student. Okay, but you did not have quantum mechanics during your BSc?
Sir, just in chemistry. I didn't have mathematics in BSc.
Okay, no, that's okay. But what about quantum mechanics? Did you have quantum mechanics in your BSc?
Yeah, sir, in the chemistry part we had that.
Yeah. Okay, whatever. Chemistry part, you had quantum mechanics. Yeah, I know there are MSc students who did BSc without mathematics. So yeah, I understand. There is a fraction. So anyway, so how many of you have watched those two videos? Tell me, how many of you have watched those two videos?
So this is Orko Prabhu.
Yes.
So I have watched it earlier actually in YouTube. It is on NPTEL, right?
What about others?
This is Aishwarya, sir. I have also watched it.
Okay, what about BA students? Devojit. Now I'll take the names. I have the list.
Yes, sir. I have watched.
You have watched.
Pretty long, but okay.
So you can teach us?
Yes, I can try maybe.
Okay, very good. Maybe next time. Okay, what about Ganpat Patel? Have you watched the videos?
No, sir. Not yet.
Okay, many are saying watched, many are saying not watched. Okay, so the whole thing is before we meet on Friday, which is day after tomorrow, you guys should go and watch those videos. You watch movies, na? So this is also not bad. Go and watch those two videos. Okay, so that is very important. Now let me start presenting something which is going to start now. I'm going to share my screen, and hopefully you can see. So can you see the screen?
Yes, sir. Yes, sir.
Yes, sir.
Okay, so let me make it full screen. So can you see it full screen?
Yes, sir.
Okay. Okay. So now let me start by saying that this course, the CH425 as well as CH812, I think both the courses could have been called quantum mechanics in chemistry. Okay. And I don't know whether you can see some equation. Okay, sorry. Some problem. Yeah. Can you see some equation there? And the arrow comes, and then another equation. So these are, you know, those equations. Some of you would know, I'm sure.
Yes, yes, sir.
This is the, yeah, this is Schrodinger equation. This is the key equation in the subject called quantum mechanics. Okay. So the theme of the course is quantum mechanics and its application in chemistry. How quantum mechanics is useful in chemistry. Okay. So as you already know that the instruction for this course is me. My name is Rajarshi, and I have an office, room number 408B, but it does not mean much with this special semester on. And my phone number is given there. So I also have my mobile number, but it is also there on WhatsApp. My email IDs and my web page, link to my web page. I look something like this. I think now I've lost weight, so I look much better. I'm going to teach the first half of the course mostly. But the second half of the course will be taught by Professor Rahul Moitra, who is an expert in quantum mechanics in chemistry. Okay. And he is also there with us in this session. And there are 5 TAs so far, and I have already introduced these TAs: Asha, Praveen, Rajiv, Ligesh, and Anish. People ask me usually recommended text. What are the books? I'll let you know. I'll email you the list of books and how to get it. We'll resolve it in next 1 or 2 weeks. And we're going to contact each other, all these documents and everything, through Moodle, a little bit on WhatsApp, but the interaction will be on Google Meet, because I like this platform, and we're going to use Google Meet for interaction. Now, let me ask this very question: why we need to study quantum mechanics? The very crude way of saying this, that this quantum mechanics is necessary to understand the processes which are happening at molecular and atomic level or subatomic level. If you are a scientist or even an engineer, you must never be a frog in the well, I always believe. So you should know many things other than what you have in your curriculum. You have to go beyond curriculum. And you're a chemist does not mean that you should not know quantum mechanics. So we'll see why quantum mechanics is so important. Even if you are doing not quantum mechanics, in your research you're doing something like organic chemistry or inorganic chemistry experiment, but it is always good, or actually it is must, to know the basic quantum mechanics, basic quantum chemistry. Without that, you cannot proceed. You cannot understand chemistry. So in order to understand chemistry, you have to know quantum mechanics. Okay. And I have a quotation from great poet Tagore. I think many of you would know this. Anyway, I'm going to share these slides. So usually the subject quantum mechanics will introduced soon, but the subject quantum mechanics is taught in physics and less in chemistry. And this will give you an idea what is being taught in physics, what is being taught in chemistry. I am having this slide because most of you, I think 95% of you, have gone through a course in quantum mechanics or quantum chemistry. Okay, so can you see the things on slides? Is it visible? Hello?
Yes, sir.
Yes, sir.
Yes, sir. It is visible.
Visible. Okay. So you'll see that will come to this something known as Schrodinger equation every time. And when it is taught in chemistry, you start with something like you see that hydrogen atom problem, where you have one electron and one nuclei, and then you go to many electron, for example helium, which has 2 electrons or higher, and then you go to molecules, from atom to molecules. And this is what usually taught in chemistry. But in physics, little bit of hydrogen atom, but then they concentrate on other topics such as tunneling, which is a quantum mechanical phenomenon, and then they move to more something like solid state physics, and they apply quantum mechanics there. They talk about band theory. In chemistry, you talk about chemical reactions. There they talk about solids and transport phenomena in solid. For all these things, you need quantum mechanics. Without quantum mechanics, you cannot understand these things. Okay. And the content of the course is schematically shown here for both the courses. So we'll start with the what is known as failure of classical mechanics. Why classical mechanics is not the theory to describe subatomic particles or subatomic world. And then we'll discuss what is known as old quantum theory, and then we'll introduce the subject called quantum mechanics through postulates. And the subject was introduced in 1925-26 by two famous physicists, Schrodinger and Heisenberg. And we'll now deal with some exactly solvable problem. These are problems which can be solved exactly. Mathematics of the problem can be solved exactly. Example is particle in a box. So I think you have done this, no? Particle in a box, most of you?
Yes, sir.
Yeah.
Yes, sir. We have done this.
And then we'll go to other things. We'll talk about perturbation and variation techniques. These are approximate methods. And then we'll talk, before that actually going to talk about hydrogen atom, quantum numbers, atomic orbitals, the concept of electron densities, the concept of spin, and then we'll talk about many electron atoms, and then molecules, where we talk about chemical bonding, such as molecular orbital theory, valence bond theory, Huckel theory, and of course eventually perturbation and variation techniques, and there will be additional topics for CH812 towards the end. Okay. Now I have this slide. How many of you have seen this slide? Tell me. Something like this. No, I'm saying not this slide, but something like this, which is shown on this slide, like atomic spectra.
Yes, sir.
How many of you have seen this?
Yes, sir. I've seen.
Okay. So why I'm showing this slide? Any idea? Any idea why I'm showing this slide?
Actually, in the case of atom or molecule, we found the discrete spectra, but above that is a continuous spectra as seen in the rainbow.
Okay. Anything else?
These cannot be explained by classical mechanics.
Classical mechanics.
It's all quantization.
Okay. So what is classical mechanics? Then I should start from classical mechanics. So what is classical mechanics? You're saying classical mechanics. So I'm asking every one of you, what is classical mechanics?
Newtonian mechanics is a very classical mechanics.
Not very classical mechanics, that is classical mechanics. So the mechanics by Newton.
Yeah.
So what is there in classical mechanics? How do you introduce classical mechanics?
There are.
So everything is a continuum there, no quantization, and
okay.
We study it at a microscopic level.
Okay. See, the point is there's a company called chicken and egg problem. Okay, you know that? Chicken and egg. You are saying there is nothing called quantization. Actually, when you do classical mechanics, you don't know anything about quantization. You don't even have the notion of quantization, isn't it? You understand what I'm saying?
Yes,
hello?
sir.
So
Yes,
let us revisit classical mechanics. Okay, so let us revisit classical mechanics. So if I write something, can you see? Let us check. This is also going to be a good check here. Can you see?
Yes, sir.
Yes, sir.
Yes, sir.
And we start with a gentleman, Newton. And the version of classical mechanics is called Newtonian mechanics. That is because of Newton. Now, what is there in Newtonian mechanics? I just go back to your school days. So for example, if I have a ball and then I apply some force on this object, can you write down the equation of motion for this object? What is that?
Is equal to ma.
Okay, you know, so basically the idea is it's a force balance, isn't it?
Yeah.
So force is given by
Mass into acceleration.
mass times acceleration. Okay, I can write like this. This is fine? This is okay?
Yes, sir.
Now I want to make it more quantitative, okay? So the force, I call it F. And the mass is M. So I have a one particle, this ball. The M is the mass of the ball. Is it okay? If anybody cannot follow, tell me. If M is fine. Okay?
Yes, sir.
And then you have to multiply this with what? Acceleration. So I assume that, okay, in general, the motion is in 3 dimensions, but make it simple, life simple, say in 1 dimension, okay? You understand?
Yes, sir.
Yes, sir.
In 1D, means 1 dimension. And that is X, that is my dimension, X dimension. So if it is in X dimension, then I have to multiply M with acceleration in X direction, X dimension, no? And what is the definition of acceleration?
Per unit time.
Square by t.
Change in velocity per unit time.
Change in velocity per unit time. So, okay, if V is velocity,
Yeah.
Square x by dt square.
this is velocity. Now, I have people who did not have background in math. For them, I'm just going to repeat this. Velocity is what? Distance traveled
Per unit time.
per unit time, no?
Distance per unit time.
Yeah. So it is going to be, if I use, what I'm going to use throughout this course, some noise is coming. I don't know from who is. So if I'm going to use this thing, for example, if x is the displacement, then if I write like this, dx dt, this is called velocity. Are you familiar, all of you?
Yes, sir.
Yes,
V is dx dt. So what about acceleration?
d2x dt.
Yeah. So d2x acceleration is actually c dot,
dv by dt.
which is dv by dt, isn't it? Dot means dv by dt. And this is equal to
d2x by dt square.
and that you should put here. And what you have now? This equation, this is called Newton's equation of motion. Okay.
Yes.
You know, all of you know, I'm sure.
Yes, sir.
Newton's equation of motion. Now, what is force? What is force? It's mass time acceleration, but is there any other way to define force?
Change in momentum with time.
Linear momentum.
Change in momentum. Hey, can you
Pressure
all
per unit
please,
area, I think.
can you all please switch off the microphone?
Yes. Maybe you can just use the chat and there you can answer.
No, whenever or maybe whenever you have to ask something, then just
Yeah.
unmute yourself. Otherwise, just keep the microphone unmuted.
Yeah. So my question is, maybe you can relate this force to some potential or potential energy.
Force is equal to dV by dx. dV by dx if U is a potential energy.
Yeah, you are almost there. So actually, your
is equal
force
to
is,
minus dV by dr.
yes, it is minus dV by dr, but in one dimension it is minus dV by
dx.
dx. And people are also saying that force is something like rate of change of momentum or something. People are saying, huh? We'll see what is that. So force is minus dV by dx. Okay. Now this is the version by what is known as Newton. This is called Newtonian mechanics. Okay. Now let me write down something like this. Now, if you have a system like the ball, so I can write the total energy of the system, isn't it?
Yes, sir.
Total energy. Now I use this symbol H for total energy, okay? Now this total energy is going to be what? Tell me.
Kinetic energy plus potential energy.
So it is going to be kinetic energy plus potential energy. Usual notation for kinetic energy is T. It is not temperature, okay? It is kinetic energy, yeah? Not temperature. And this potential energy is either V or U. So let it put it like this. So H is equal to T plus V. But again, you go to your school physics. What is kinetic energy? If I write explicitly,
half mv
square.
Half mv square. Let me write down half mv square. This V is small v, huh? And this is capital V, okay? So don't mix it, huh? This is capital V, which is potential. Now half mv square, you remember there's something called momentum, linear momentum, P. This is mass times velocity, isn't it? So if I use this relation and put it there, what I'm going to get something like this one is going to be half mv whole square divided by m.
P square by m. Half P square by m.
So basically, it gives you
Half P square by
2m.
M plus P, which is your H. And this H is called total energy, or also called the Hamiltonian of the system.
Hamiltonian operator.
This is not operator, okay?
Okay, sir.
You are doing classical mechanics. It is still Hamiltonian. Okay, this is fine. Is this fine?
Yes,
Okay,
sir.
now let me do one
Yes, sir.
thing. Now this Hamiltonian is a function of momentum as well as V. V is potential. Now this V is potential means it is a function of only position. This is V of x, isn't it? It depends on what position you are in. For example, if this is your x direction, and if I put a ball here, which is at a height, say h, from ground, then what is the potential? You know,
MGH
m g
into G into H. G is a gravity acceleration.
h is like your x, isn't it? So
Yeah.
v is a function of h. Here, in general, v is a function of x. Or you have a harmonic oscillator like this, and you have particle trapped in harmonic oscillator. Okay, it has a restoring force. No, it will come like this, come to bottom. And what is the any harmonic oscillator potential? You know that Vx is
half k prime x square.
half kx square. So V is a function of x. It has nothing to do with momentum, your potential energy. Okay, it is a
Yes,
function
sir.
of position only. So your Hamiltonian, you have two parts. One part is function of momentum or velocity. Another part is function of position. Is it clear?
Yes, sir.
Is it clear? Okay.
Yes, sir.
So now let us go. And if I take this Hamiltonian and take a derivative of this Hamiltonian with respect to momentum, linear momentum. So I have this notation, which basically means partial derivative by keeping x constant. So what is the answer on your left?
Coordinate means X. If it is one dimension, so it have to be X.
P by m.
See, it is going to be, you have to multiply, what do you have? 1 by 2m is constant. So you have to differentiate p square with respect to p.
It will
It is
become
going to be
2p.
P by
and the next term is 0 because it has nothing to do with momentum, isn't it?
Yes,
So
sir.
what you have is,
P by m.
sorry, p by m plus 0. Okay, I don't need to write plus 0, p by m. What is p by m?
Is equal to
Velocity.
Velocity, because p is m into v. And what is velocity?
Velocity.
dx
X dot.
dx dt.
Or dx dt, huh? Okay,
Yes,
this is
sir.
good. One thing you get. Now, if I do the same thing, but now we just similar thing, but I now take a derivative of this with respect to x. What I'm going to get? What I'm going to get? Now, this part is independent of x, no? Kinetic energy.
0
P
plus
square.
del b.
So it is going to be
0 plus kx.
not kx. Just look at del v del x. Kx is an example in general. In general, okay, del v del x or dv dx actually. And anyway, so this is going to be, and this dv dx I told you that it is going to be minus of force, isn't it? Okay, it is minus force, and
Yes,
this is equal to force is nothing but, you know, what is that?
Mass into acceleration.
It is actually rate of change of momentum, isn't it?
Momentum. Yeah. Yes, sir.
Minus
Yeah.
p dot.
P dot. Yeah.
So now end of the day, what I have two equations. Just look at it. One is this. This del H del P is equal to x dot. Huh? And the other one is del H del X is equal to
Minus p dot.
minus p dot. So this is also like Newton's equation, but this is slightly different. And but it's equivalent, and this representation is called these two equations together. So if I write it down, for example, I don't need this. So let me write it here. If I do it for a 3D in general case, it should be like del H del P is equal to say Q dot. Q is the position. Q dot. Q is like X, and del H del Q is equal to minus P dot. And these two equations together is called another equation. You know the name?
Hamilton.
Yeah, this is called Hamilton's equation of motion. Okay. By another scientist. But what you have seen that, okay, in classical mechanics, we have assumed, or the case is that we know the position and the momentum precisely, accurately,
Yes, sir.
isn't it?
Yes,
Because
sir.
I am saying it has a position X, where is that X, or Q here, and momentum P. It is precise. I know if the particle is here, I know it is here. I know what is the momentum. Okay, if the particle is here, I know what is the momentum, what is the position. So I know the momentum and the position at the same time without any uncertainty. Okay, this is clear in classical mechanics because there is no restriction. You are saying it is. So at any time I can describe the system with its position and momentum in one dimension, or in 3D
Yes, sir.
with your Q and P. Q is also sometimes called R. R is like XYZ. XYZ. But I know the position and the momentum of the particle at that instant without any uncertainty. This is classical mechanics. So in the next class, we will see that how it is not the case with quantum mechanics. So the whole thing is in classical mechanics, position and the momentum of the particle is not is, I think, R. Are known simultaneously without any it's fine, which basically means the whole thing is called deterministic. How many of you understand what I'm saying? Tell me. If there is anyone who does not understand, please let me know. What I'm saying that, okay, in classical mechanics, things are deterministic. Hello, are you there?
Yes, sir, we are there.
Yes. Now, deterministic means at any instant, if I have a particle, I know its position X, I know its momentum P, and if I know it now, I also know what will be the position and momentum at some later time. So it is known without uncertainty. I know it is here with this momentum. I know exactly what is the momentum value, what is the value, what is the position. Okay, there is no ambiguity. So that is why it is called certain. There is no uncertainty in classical mechanics. And also one more thing, you must have observed that I said that okay, this P, if you give me a value of P, I'll know what is the kinetic energy. Kinetic energy is what? It is P square by twice M. So now the P has no restriction. In general. And as a result, your kinetic energy could be anything, no? Any positive value. It could be 0 if momentum is 0. You understand? So any kinetic energy could be of any positive value. Give me a value of M, you know the value of P. You put it there, get the kinetic energy. And there is no restriction on momentum. So if I put more and more force, then momentum will increase, isn't it? And as a result, there is no restriction on P square by twice M. So kinetic energy has no restriction in classical mechanics. So as potential energy in general. This is fine. But we will see in the next class that when you introduce this subject, beautiful subject of quantum mechanics, we'll see in the next class that this is not the case with quantum mechanics. So this is sorry for my handwriting because I'm practicing. So this is not the case with quantum mechanics. And you already know, no? Some of you. What is the case with quantum mechanics?
They are measured with some uncertainty.
Uncertainty. So that is the main thing in quantum mechanics. The uncertainty. Because without certainty, we don't know the position and the corresponding momentum. Okay. At the same time. And there's something called Heisenberg's uncertainty principle, which we'll discuss, definitely we'll discuss. I think we'll stop today. Okay. I'll stop presenting, but for next few minutes, you can ask me questions if you have. Shall I stop presenting? Okay. Stop presenting. And please let me know if you have questions. Now, after today's video, go and watch the videos by Professor Sebastian, video 1 and video 2.
Sir?
Any question? Yes, please.
Sir, in MSc, we studied this one thing, Lagrangian equation of motion.
Yeah.
So actually, sir, what is the absolute difference between Newtonian, Lagrangian, and Hamiltonian equations of motion?
They are equivalent, but there are some advantages using Hamiltonian's equation of motion, Lagrangian equation of motion over Newtonian equation of motion. And these are technical things, okay, but they are equivalent, okay.
Yes, sir.
Like in quantum mechanics, you have different formulations of quantum mechanics. So like in classical mechanics, you have different approaches. They're equivalent, but they're sometimes actually Hamilton equation of motion is quite useful sometimes. Lagrangian equation of motion is quite useful. Newton's equation of motion becomes complicated when you deal with two-particle system. Maybe sometimes it is useful or very advantageous to use Lagrangian equation of motion. These are technical things. Okay, we can talk later. Okay, but they are equivalent. Yes, the whole thing is they're equivalent. There is no difference between these two.
Thank you.
Okay.
Hello, sir.
Yeah.
So I have a question that how we can determine that this potential thing depends only on position or position and time.
No, I am assuming that it does not depend on time. We'll deal with time as well. Now, time means you have to have a potential which is, say, for example, changing with time. But here I am assuming the potential does not change with time. So if you have a closed system from within, then your potential has no time dependence. And only when you disturb your system or part of your system externally, then that brings an additional time dependence to your potential. Like if I apply a magnetic field or an electric field from outside, then that would make my potential time dependent. Otherwise, from within, it is time independent. For example, in hydrogen atom, we have nucleus and we have electron. The potential is time independent. It's 1/r. But when you take the hydrogen atom, put it under say a magnetic field, then it will be time dependent potential because of this magnetic field. Some oscillating magnetic field, for example, oscillating electric field, then it will be time dependent. How you design. But from within, there is no time dependence. Okay. So how an electron interacts with the nucleus now and after 100 years does not change with time. It is given by a functional form, and that remains unchanged. It is independent of your observation, whether your time of observation, whether you're calculating now or later. So there is no time dependence in the potential. Okay, Shumesh?
Okay, thank you.
Yeah, but we'll see how the time dependence can come. So I'm talking about potential, which is time independent completely. Okay. We'll talk about time dependent potential. But even if it is time dependent, you see that I took derivative with respect to position and momentum. I did not take derivative with respect to time in that sense. Yeah, so time is not directly involved in Hamilton equation of motion. It is there because it's equivalent to rate of change of position, rate of change of momentum, but we don't take a time derivative of the Hamiltonian. So in that sense, it is fine. Okay. So anyone else has a question? So what I'm going to do, I'm going to send this video later today. Maybe I'll name it and then put it in a folder and share the link to the folder. And you guys can download, and I'll keep it in the folder for next 4 or 5 days. Then I'll remove. So next 4 or 5 days, you just download that video. Some of you can download, then they can distribute this, but don't distribute this to anyone who is not registered for this course. So all these videos are only for internal use, only for you guys who are registered for this course, IIT Bombay students. Okay? Is this fine? So shall we just wrap up today? And we'll have next session this Friday, same time, 11 to 12:30. But please watch both the videos, and in the next class we will discuss those videos. Okay. Okay. So thank you very much, and be safe and healthy. Go and have your lunch, and thank you very much for joining. Okay. Okay. So I think I'm going to now stop recording.
Yes, sir. Thank you.